Hi students, now we're going to talk about endothermic reactions and have a look at what characterizes an endothermic reaction, looking at the heat and energy in the reaction. So endothermic reactions are the opposite of exothermic reactions, and in an endothermic reaction, heat is being absorbed into the system. So energy or heat from the surroundings is being absorbed into the system such that the products have absorbed that energy. So when we look at an endothermic reaction, and again, there's a little bit of a memory trick that we can use here, just like for exothermic reactions, where the EX in an exothermic reaction can be used to remind us that heat exits the system. The same is true here. So for an endothermic reaction, the EN in endo can help us remember that heat enters the system. So let's take a look at a simple example of an endothermic reaction, and then let's talk about a few other examples that we see in daily life. So here below we have a reaction equation, and we've got HCl, the compound HCl, that's our reactant, is changing to an H atom and a chlorine atom. So this is a process in which we have bond breaking happening. The HCl covalent bond has broken so that we now have a hydrogen atom and a chlorine atom separately. And bond breaking is a process that requires energy. We must put energy into the system in order to break that bond and overcome the strength of the covalent bond. And so we see the energy on the reactant side for an endothermic reaction. So this is always true. Okay, our energy term, okay, will appear on the left-hand side or on the reactant side. The easiest way to think of it is it's on the reactant side. So energy is much like a reactant. We need to put it in order to get to our products. So we can really, in a simple way, we can really think about energy as being a reactant for an endothermic reaction and as a product for an exothermic reaction. So at the end of our reaction then, because energy has been absorbed into the system, the energy of our reactants, or our products, pardon me, at the end is higher than the energy of our reactants from where we started. So energy has been absorbed, and now we have higher energy products as a result. And we need to be a little bit careful when we're talking about endothermic reactions, because we're talking about heat, and it's very, very easy for a student to mix up the difference between temperature and heat. And so when we're talking about heat, heat is a type of energy that can be transferred from the surroundings into a system, from one chemical species to another. And when we're talking about temperature, temperature is actually a measurement of the kinetic energy that a particular species has. So it is different from heat. So we just need to be a little bit careful here that when we're talking about absorbing heat or absorbing energy, what is happening to that energy? In this reaction here, and I'll just write it out again, a little bit bigger, I'll use E for energy. What's happening to that energy? Okay, this energy here that we have to put into the system for this reaction to happen is going towards breaking the bonds. So it is not the case that we're going to have really, really hot products at the end. Okay, we're not going to necessarily be, we're not seeing a temperature rise in our system. In fact, we will be seeing the temperature of our system potentially go down for an endothermic reaction. So the energy that we're putting into the system is being used up for something. And here, when the energy is absorbed, it's absorbed into the products so that we have used it to break those bonds, and those products have higher stored energy or higher potential energy. They are less stable and they have a higher energy at the end of the reaction. So it's just really important to make that clear note here that we don't want to think about endothermic reactions as reactions where the temperature always goes up, okay, of the reactant, because that is not the case. Let's have a look at a potential energy diagram so that we can think about in a visual way what's happening in an endothermic reaction. So we'll go ahead and you do a really generic one here. And again, I'm plotting my potential energy, which is my stored energy here on the y-axis. And on the x-axis, I'm watching my reaction proceed, just like a story from left to right. And so in an endothermic reaction, we are starting with our reactants, and we are moving to products which have more energy. So this is going to be an uphill curve when I look at my diagram. So we're starting from some reactants down here, and all endothermic reactions will have the same general shape. Of course, the specific amount of potential energy that the reactants and products have will depend on the actual reaction. So this little line could be at different points, but we're always going uphill in an endothermic reaction. So we have to put energy into the system, and we're going to see our energy or heat term in kilojoules on the left-hand side, on the reactant side. So we put the heat in, and that heat then is being used, and we are producing a product, or perhaps more than one product, that has a greater amount of stored or potential energy compared to our reactants. So the net change in energy here is positive, and we are going uphill, okay, from our reactants to our products. There's not as many examples that we see every day. There's lots of exothermic reactions that we can think about. We talked about exothermic reactions. Combustion reactions, for example, are really common and happen in many practical things that we see and use. In endothermic reactions, there's not as many that you might be able to think of off the top of your head. Cold packs are an example of an endothermic reaction. If you've ever used a cold pack before, it's one where the chemicals are separated within the little package, and when you squeeze it or break the barrier, the chemicals are allowed to interact, and when they do so, the reaction is endothermic. So what actually happens is that energy from the surroundings is absorbed by the system, by the cold pack, and it's absorbed to break the bonds and form a new product inside the cold pack. And what we actually find happens is that when you're holding the cold pack, you'll feel the package getting colder as the reaction happens. And that is characteristic of an endothermic reaction. It almost seems a bit counterintuitive when you think about it, but we have to remember that we're talking about stored energy here. Okay, not temperature. And so the stored energy is or energy from the surroundings is being used, and we have more stored energy in our products. So we've taken away some of that energy in the form of heat, and it's now stored energy. And so cold packs are a good example of that. And we feel it actually getting colder in our hand as this reaction that we see proceeds. Another good example of just an everyday reaction, this is not a chemical reaction, but a great example of a phase change, is the melting of ice. So melting ice, if you put some ice in your cup of water and you watch it melt, or you hold it in your hand and you watch it melt, this is a very simple phase change in which we are moving from solid water to liquid water. And in order to change from solid water to liquid water, we need to have some energy present. We must put heat or energy into the system. And so we see the heat on the reactant side. And the solid water will use some of the energy from the surroundings in the form of heat to break some of the attractive forces between the solid water molecules and separate in order to become a liquid substance. And so in doing so, we are actually putting energy into the system. It's entering the system from the surroundings to give us water, liquid water. And here is the potential energy diagram for melting ice, where we have the reactant as our solid, and again we're seeing that change in potential energy going up as we form our products, and so our liquid water has higher potential energy. So let's do a really quick summary then, looking at an endothermic reaction. So we've talked about a few different things here. So again, the memory clue that you might find helpful is that for endo reactions, the heat enters the system, okay, or energy enters the system. When you're looking at an equation, it's important to remember for an endothermic, we're always going to see the heat term or the energy term on the reactant side, because it has to be put in to get to our products. Remember, energy is being used up or absorbed here, so we are always going to see our heat or energy in kilojoules on the reactant side. Okay, and when we look at a potential energy diagram, the shape is always going to be the same when we look at the curve, and we are always going from our reactants uphill to our products, and the change in potential energy is going to be positive here. So as we move from reactants to products, we have to use up or absorb energy in order to get there. So this is a nice clear summary for an endothermic reaction.